Today we are exploring interface phenomena. An interface is essentially the surface boundary that exists between two different phases, such as solid, liquid, or liquid gas, and also in between the liquid and also the liquid interface. In this context, we will focus on adsorption, which is a reaction that occurs specifically at this surface. So, what is adsorption? It is a tendency of molecular species to occupy a surface. We utilize this process to separate components from a liquid or gas by collecting them on a solid surface. For instance, activated charcoal is commonly used to adsorb gases like hydrogen, oxygen, and nitrogen. Why does the process of adsorption happen? Molecules at the surface of a liquid or solid are in a different environment than those in the bulk. A molecule at the surface is surrounded by its own phase on one side and also by a fewer molecules from the gaseous phase on the other side. This creates unbalanced forces compared to those molecules which exist in the bulk medium. So these unbalanced forces create a net inward force of attractions that pulling those surface molecules inward. Due to the net inward force of attractions, it allows the molecule to be pulled on the surface of the substrate. Adsorption can occur on various types of surfaces. For example, if you have a solid charcoal in a closed vessel and trapped with oxygen gases, the molecules will adsorb onto the charcoal surface, increasing the gas concentrations there. Similarly, if a liquid is placed in the vessel, oxygen molecules will adsorb at the liquid surface. To discuss the adsorption scientifically, we need two terms. The adsorbent is the substrate or surface where adsorption occurs. The adsorbate is the molecular species that actually accumulates on the surface. Commercial adsorbents are usually highly porous, offering massive surface area. Sometimes it can go up to 1,200 meters square per gram. So the VSEM images here shows the morphology of charcoal with the presence of the pores in the charcoal. We see adsorption daily. Think of dust particles accumulate on clothes or various environmental gases collecting on the surface of charcoal. In these cases, the clothes or the charcoal act as the adsorbent, while the dust or the gas is the adsorbate. It is important not to confuse adsorption with absorption. Adsorption is strictly a surface phenomenon. Conversely, absorption is a bulk phenomenon, where the substance is uniformly distributed throughout the entire volume of the material. Consider a piece of chalk dipped in ink. The ink pigment stays on the surface, that is adsorption. However, if you break the chalk, you will see inside is wet but white. The solvent, which is water, has moved into the bulk, which is absorption. Another great comparison involves water vapor. Silica gel adsorbs water's molecule onto its surface. In contrast, if you put the calcium chloride in a vessel, the calcium chlorides absorb the vapor, and the vapor actually passes through the surface to distribute throughout the solid. In lab and industry, we frequently use charcoal, silica gel, alumina gel, and clay as adsorbent due to their high surface affinity. In addition to the term of adsorption, absorptions, there are also have the desorptions and also sorption. Sometimes both adsorption and absorption happen at once, so we call this sorption. If you want to remove the adsorbed substance from the surface, the process is called desorption. This is typically achieved at high temperature and low pressure. The effectiveness of the adsorbent is largely tied to its surface area. A larger surface area relative to the weight of the adsorbent allows for a much greater extent of adsorption. What holds the adsorbate to the surface? The attraction is caused by intermolecular forces such as van der Waals forces or hydrophobic interactions. This affinity depends on the molecular size, shape, polarity, and the system temperatures as well as the pressure. As mentioned earlier, desorption is the removal of substance from the surface by reducing the pressure or increasing the temperature. We provide the energy or environment needed for molecules to leave the adsorbent. How do molecules bond to the surfaces? There are two primary ways molecules bond to surfaces: physical adsorption, or known as the physisorption, and chemical adsorption, or known as chemisorption. The distinction lies entirely in the nature of the bonding. In physisorption, the interaction is based on weak van der Waals forces. Because these energies are low, which is similar to the enthalpy of condensation. So the molecule lose energy as they bounce across the surface until they are accommodated or adsorbed. Usually, think of gas molecules resting lightly on a solid surface, where they are held by the weak forces, which is the van der Waals forces. And the classic example is dihydrogen molecules on the surface like platinum. Because the enthalpy of physisorption is low, which is around 20 kJ per mole, therefore it is insufficient to break the chemical bonds, and the molecule will retain its identity, and there is no significant change in the electron density. In contrast, chemisorption involves the formations of an actual chemical bond, usually the covalent bond between the adsorbate and the surface. So this involves a substantial rearrangement of the electron density and has a much higher enthalpy, around 200 kJ per mole. When we compare physisorption and chemisorption bond, while physisorption relies on weak forces at low temperature. In contrast, chemisorption often requires high temperature to form the strong either ionic or covalent bond with the adsorbent. In addition, for chemisorption, the distance between the surface and the adsorbate is much shorter. Interestingly, the surface atoms demand for satisfied valencies, and it can be so strong that they tear the adsorbate molecules apart, and resulting in the molecular fragments on the surface. Next, to quantify adsorption, we use coverage or the extent of surface coverage, represented with the lowercase grade theta. So it is defined as the ratio of the occupied adsorption sites to the total available sites. The extent of surface coverage can be expressed by volume relative to the volume required for a complete monolayer formation, while the rate of adsorption d theta dt is the rate change of the surface coverage. It can be determined by observing the change in the fractional coverage with respect to time. Generally, adsorption is an exothermic process, meaning that it releases energy with delta H equals to negative. Since molecules become more ordered on the surface, therefore the entropy delta S is decreases after the process of adsorptions. So delta S also become negative. The adsorption is a process of spontaneous because the delta G is negative. Occasionally, chemisorption can be endothermic where the delta H is positive. So this happens if the adsorbate dissociates and becomes highly mobile on the surface. The example is like hydrogen adsorbing on glass. In this case of the hydrogen on glass, even though heat is absorbed, the process is possible because the increase in the entropy from the moving atoms is large enough to keep the delta G negative. The enthalpy of adsorption depends on the extent of surface coverage. Because the adsorbate particles interact with the adsorbent. If the particles repel the adsorbent, for example, carbon monoxide repel the surface of palladium, then the adsorptions will become less exothermic when the coverage increases. But if the adsorbate particles attracted to the surface or the adsorbent, then they tend to form the cluster. And these adsorbates also shows order-disorder transitions when they are heated enough for thermal motions to overcome the particle-particle interactions. However, it is not so much that they can be dissolved. Now let's look into some of the characteristics for the adsorptions. Specificity of the adsorbent. Visisorption has no specific preference for any gas because van der Waals forces are universal, while chemisorption, however, is highly specific. It only occurs if the right chemical bonding is possible. The amount of gas visisorbed depends on the nature of the gas itself. Different gases will adsorb to different extents, even on the same adsorbent at the same temperature. So the nature of the adsorbate will also determine the process of adsorption. In this example, we have sulfur dioxide, methane, and hydrogen gas as the adsorbate on the adsorbent, which is the charcoal. So all these three types of the gases, they have the different critical temperature, which is defined as the highest temperature at which a substance can exist as liquid. So above the critical temperature, the substance will exist in the gas phase. Sulfur dioxide has the highest critical temperature. So we will see that the adsorptions of sulfur dioxide on the charcoal is comparatively much more compared to the hydrogen as well as the methane gas. The liquefied conditions allow the sulfur dioxide to have a strong interactions with the surface. Therefore, it allows the greater adsorptions compared to the others. So this is the effect of the nature of the adsorbate on the process of adsorptions. And now you can read through this slide to justify why sulfur dioxide it has a higher extent of surface coverage compared to the other two types of the gases. Reversibility of the process. Adsorption is a process involving equilibrium, so the process of adsorption and desorption will occur simultaneously until they achieve equilibrium. For physisorptions, because it is an exothermic process based on the weak forces, so it is generally will produce heat upon the process of adsorption, while the substrate adsorbed will be desorbed and absorb heat. Therefore, according to Le Chatelier principle, if we increase the pressure of the system, as in this example, or decrease the temperature, then the system will try to shift to the equilibrium where it can reduce the pressure as well as to increase the temperature of the system by moving forward, thereby it increasing the adsorption. Conversely, when the pressure is decreased or temperature is increased, then the equilibrium will shift backwards so that the system will try to increase the pressure and decrease the temperature, and this will cause the adsorption process to decreases. Physical adsorption is reversible due to the weak van der Waals forces of attractions between the adsorbate and also the adsorbent. Unlike physisorption, chemisorption is usually irreversible because of the strong chemical bonds formed between the adsorbate and also the adsorbent. For example, oxygen gas is chemically adsorbed on the carbon. When we heat up the surface, the oxygen doesn't just come off as gas oxygen. Instead, it will turn to produce carbon monoxide and carbon dioxide. So, the chemisorption is an irreversible process. Requirement of activations energy, where activations energy is the minimum energy required to convert the reactant to the respective products. In the physisorptions, it requires no activations energy because there is no bonds are formed. But for chemisorption, it requires activations energy to facilitate the formations of chemical bonds between the adsorbent and also the adsorbate. Hence, the physisorption is favored at lower temperature, while the chemisorption requires high temperatures to overcome the activations energy barrier for the bond formations. The example here shows that on a nickel surface, hydrogen may first undergo physisorption as molecules at low temperature. As the temperature increases, it transitions to chemisorptions, where the molecules may dissociate into atoms. Layers of adsorptions. In physisorptions, multiple layers of molecules can stack on top of each other, held by van der Waals forces. In chemisorption, the interactions only occurs with molecules in direct contact with the surface, so only a single or unimolecular layer is formed. Next is the surface area of the adsorbent. The greater the surface area, the greater the adsorptions. This is why porous structures like charcoal make such excellent adsorbents for both types of adsorptions. Some materials are microporous, meaning the surface effectively extends deep inside the solid. Zeolites are prime example. This is the physical appearance of zeolite. They are aluminosilicates with cavities where small molecules like carbon dioxide and also like ammonia, it can be adsorbed internally. Zeolite is used in the petrochemical industry. Certain acidic zeolites that it catalyzes the reactions like dehydrations of the methanol into gasolines or the isomerizations of the xylene by acting as a Bronsted or Lewis acid. So the catalytically important from this acidic zeolite may be either a Bronsted acid or Lewis acid. Therefore, it will allow the absorptions of the liquid on the porous structure on these zeolites to help in the process of catalysis or the respective applications.